Hi everyone, so I'm Haley and this video is going to be about Voltaic cells. So for our practice problem, complete the following Voltaic cells applying the standard reduction potentials given. So our top chart are standard reduction potentials and our bottom chart is what we're trying to fill out today. So we're looking for the cell notation and the E of cell of these reactions. I think it's important to keep in mind what E of cell is. So E of cell, for voltaic cells and galvanic cells, we want our E of cell to be a positive number. Remember that E of cell is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. So in order to find a positive E of cell, we have to use the chart above in order to rearrange this equation so that our cathode minus our anode turns out to be a positive number. A few little notes about reduction potential before we start is that if we have a high standard reduction potential, so that would be a very large positive number, we know that the species is going to be a strong oxidizing agent. And what this really means is that the species wants to be reduced. And taking that even further, the species wants to gain electrons. So conversely, if we have a low standard reduction potential or a large negative standard reduction potential, we have a strong reducing agent. Or something that wants to be oxidized or lose electrons. So in that case, things with low reduction potentials are species that want to be an anode, right? Because anodes are oxidized and cathodes are reduced. So something with a high standard reduction potential would be more likely to be a cathode than an anode, whereas something with a low reduction potential would be more likely to be an anode than a cathode. So in that case, we are looking at gold and iron for our first reaction, and we go to the standard reduction potentials to see that gold is 1.5 volts and that iron is negative 0.44. So in this case, we have to think of how can we get a positive number if we combine these two standard reduction potentials. So I would put the larger positive number first, so 1.50, minus our negative standard reduction potential, so that the negative signs can cancel out and be positive. So we can add 1.5 to 0.44 and get 194 as our E of cell. And in this case, when we write out the cell notation, we should know that it's anode, salt bridge to cathode. And based on where we put our standard reduction potentials in the E cell, we know that our anode is going to be iron because it is oxidized. And we know that our cathode is going to be gold because it's reduced. So in that case, we can put our anode first in its solid form, which is FeS, separated by a phase to its aqueous form, which is Fe2+, 2+ coming from the standard reduction potential chart. Then we have the salt bridge. We will have Au in its ionic form, so that's 3+, again from the table above, and Au in its solid form. So now we can move on to the second one, which is magnesium and zinc. And it seems that magnesium and zinc have standard reduction potentials of -2 and -0.7, respectively. So in that case, which one should be the cathode and which one should be the anode so we can still get a positive number? In this case, you want to put the more negative number as the anode so that it can be crossed out and we can put a positive number so that we can create a positive number for this EF cell. So in that case, we'd put -2 as our anode and -0.76 as our cathode. And we will get 1.61 as our volts. Conceptually, this makes sense, right? Because our magnesium, as we said before, has a low standard reduction potential or a large non-positive standard reduction potential, which means it wants to be oxidized, it wants to lose its electrons, and therefore it's actually a better anode than zinc would be, because zinc is more positive or is a smaller negative number, meaning it's actually better at being an oxidizing agent than it is at being a reducing agent when compared to our magnesium. So for our anode-cathode cell notation, I have the salt bridge, and our anode is going to be magnesium, so Mg2+, and then our cathode is going to be Zn2+, and Zn solid. So in that case, we can move on to our third. So our third seems to be lithium and hydrogen. So as you know, hydrogen is the basis of all standard reduction potentials. So hydrogen's standard reduction potential would just be 0. And in this case, lithium is -3. So lithium having a standard reduction potential of -3, that's a very large non-positive number, would probably want to be oxidized, making it a good reducing agent. So that would probably be in the anode position, which makes sense because if we do 0 minus a negative number, a -3.05, we can get our positive number, which would be 3.05 volts. And in that case, lithium becomes our anode, and we can put it first. So lithium, Li+, and H+, to H2. And that's it for this video. Make sure to sign in, and if you have any questions, you can always email us.